Hello everyone. I am pleased to introduce our CVPR 2026 work, Geometrically Constrained Agent for Spatial Reasoning. We call the method GCA, short for Geometrically Constrained Agent. GCA enables more reliable and verifiable spatial reasoning across diverse benchmarks and VLM backbones. The central problem is the semantic to geometric gap in vision language models. Spatial reasoning often requires fine-grained geometry, such as object orientation, viewpoint, or camera frame. But a VLM usually compresses visual input into textual semantics, which can distort the geometry needed for a correct answer. For example, when a query asks, "Sitting on the sofa, where is the table relative to you?" the model may understand the sentence, but it may still fail to determine the sofa orientation. The problem definition is wrong before computation begins. Existing approaches do not fully solve this. Training-based spatial VLMs may inherit flawed supervision from imperfect oracles. Tool-using agents can call geometry tools, but may still plan from unconstrained semantic assumptions. GCA addresses this by making the problem definition explicit before computation. The key idea is a formal task constraint, which has two parts. The first part is the reference constraint. It defines where we measure from, or more precisely, the reference frame for the answer. This frame can be object-based, camera-based, or direction-based. The second part is the objective constraint. It defines what must be measured within that frame, such as a relationship, direction, or distance. Together, the task constraint separates what to solve from how to solve it. This is the main design principle of GCA. The agent follows a two-stage workflow. In stage 1, task formalization. The VLM acts as a semantic analyst. It reads the query and images, then translates ambiguous spatial language into the task constraint. The goal is to identify the non-negotiable reference constraint and objective constraint. In stage 2, constrained geometric computation, the VLM acts as a constrained task solver. It acquires geometry through tools such as reconstruction, detection, segmentation, object orientation, and code execution. All tool calls and code must satisfy the fixed task constraint. This gives us constrained geometric computation. The VLM no longer has to imagine high-fidelity geometry inside its lossy semantic space. Instead, it binds symbols to measured geometry and computes the answer. The results support this idea. Across multiple spatial reasoning benchmarks, GCA establishes new state-of-the-art performance. It reaches about 65% average accuracy, with clear gains on challenging multi-step settings such as MMSI Bench and MindCube. The ablations show where the improvement comes from. GCA improves different VLM backbones over chain-of-thought-only reasoning. Formal task constraints outperform unconstrained and prompt-guided tool use, and approach human oracle formalization. Tool integration, knowledge-augmented code generation, and visual feedback help steadily, but the task constraint gives the largest gain. Now let us walk through one representative case study. The query asks for the direction of the glass coffee table relative to the book. A vanilla chain-of-thought model reasons semantically from the two images, but ends with the wrong answer. GCA first formalizes the constraint. The phrase, "wine glass is north of the book," defines a direction-based reference frame. Positive Z is the book to wine glass vector. The objective is the coffee table position relative to the book. Then GCA reconstructs the scene. It detects the glass, book, and table, selects the correct wine glass, segments the objects, and extracts 3D point clouds. The generated code uses these centroids to build the book to wine glass reference frame, projects the table displacement, and maps the result to the answer choices. Execution returns C, southwest. The trace remains inspectable. To conclude, GCA turns ambiguous spatial queries into explicit task constraints. The reference constraint fixes where to measure from, and the objective constraint fixes what to measure. The agent then acquires geometry and executes code under that fixed constraint. This constrained first paradigm bridges the semantic to geometric gap without task-specific fine-tuning. It improves spatial reasoning across benchmarks, VLM backbones, and multi-image settings. More broadly, it suggests that robust spatial intelligence depends not only on stronger models, but also on making the geometric problem definition explicit before reasoning begins.